Okay, it's like okay, let's start. So welcome back guys, welcome to NEET World of Physics. So we were dealing with the chapter work, energy and power right now. Work, energy and power. So yesterday we were discussing about the problem, no, like after completing the kinetic energy, we were discussing about the problem which I gave as a homework right now. So we'll discuss the answer for that question now. Yes, like we have not started with potential energy, but I have told the formula for potential energy to use in this question right now. So it is well known that a raindrop falls under the influence of the downward gravitational force and opposing resistive force. The latter is known to be proportional to the speed of a drop, but it in otherwise undetermined. Consider a drop of mass 1 gram falling from a height of 1 kilometer. It hits the ground with a speed of 50 meter per second. So what will be the initial velocity? It is 0. Initially it will be 0. It is going with 50 meter per second, like hitting the ground. Hits the ground, no. It's like ground is there. So before hitting, in the sense like it is final velocity that they have given. So initially it is 0. Okay. So what is the work done by the gravitational force, one thing, and what is the work done by the unknown resistive force? Okay. So here first we need to find the work done by the gravitational force, which is nothing but mgh. Okay. So mass they have given 1 gram, which is nothing but 1 gram should be equals to 1 into 10 power minus 3 kilogram, right? Now 1 by 1000, that's it. And g they have given 10 and height is 10 power minus 3. It is 10 power 3, sir. It is kilometer only, no? Yeah. So 10 power 3. Okay. So 10 power minus 3 and 10 power 3 will get cancelled. So remaining 10 joules. It is the work done by the gravitational, right? No. Now I need to find the work done by the unknown resistive force. No. Unknown resistive force. So now if you see what is the work done by the unknown resistive force. So the sum of work done by gravitational resistive force will be equals to change in kinetic energy. So change in kinetic energy means like kinetic energy final minus kinetic energy initial. So we know the formula that kinetic energy is equals to half mv square, where v initial is 0, v final is 50 meter per seconds. Okay, and we'll substitute those values, and we know that the value of gravitational work done by gravitation, right? No, and we don't know that work done by unknown resistive force. So this is the thing we need to find it. Okay, so of m v final, okay, v square, here u square they have taken. Okay, if you are considering both as v, mention that it is final or initial. Okay, so final minus initial. So I can neglect this out now, totally it is 0. So of 10 power minus 20 into 50 square, and this is 10 plus unknown resistive force. Okay, so we'll get the answer as minus 8.75 joules. Take it down. So why they have given it is in minus? So resistive force acting on the drop in the opposite to its displacement. Okay, it's a resistive, no? So once you have done, we'll go for the next part of the chapter. Yes, it's get cancelled, no. So this one will be cancelled off. So this one like 0 multiplied by other number will be get cancelled off, no. Total will be 0. Okay. So the remaining thing you can calculate it. Okay. So 50 into 50. 2500
divided by 2. 1.0.
Okay. Done. Now, since we are dealing with work done by the constant force, that is the formula work done equals to
FD cos
F dot D or FD cos theta. Now we are dealing with the variable forces. Okay, variable forces. So here they have given a graph, like consider a graph between the variable force and displacement. Like the force varies when the displacement occurs here. Okay. Area of the shaded rectangle, that is f of x into dx. Like let me take a small part of the displacement here. So what is the force here? F. If I consider another point here, this like it is delta x1. Again here the force will be different. Yes, no. Again if I consider some other point delta x2, so again it will be different. So when I consider the each and every point, no, if I club together I'll get a sum of work done for the given object or given question. So for that the formula is, so work done will be integral of x, like x initial to x final, f of x dx. Okay. So this is the formula for the work done for the variable forces. Done. So now one more type I will explain here, like the work, if they are asking in the question, like they have mentioned force and displacement. Okay. Now they are mentioning that some graph, I need to find the work done, like force into displacement will be work done, right? No. So I should take the area under the graph. No, I should take the area under the graph. So here what I will do is, I should consider the above x-axis as positive and below x-axis as negative. Okay. For example, so this is the node point. So above x-axis we should consider work done as positive and below x-axis it is negative. So we will take a question over here. So the question is, I need to find the work done for the given diagram. Okay. So let me take this as force and this is a displacement, right? Now I will mention some random numbers here.
10.
So this is okay 10. Here I will take this is 5 and this is 7 and this is 9. Okay. Okay, fine. This one I will take it as -5. Okay. Now I need to find the work done here now. Okay. Find it first. I need to take the area of the first shape, second shape and the third shape, and what I should do, the upper part as positive down as negative. Okay, do it fast.
joules.
20. That's it. Okay, we'll check it the answer. We'll see. So area of the triangle is half into base into height, right? No, so half base is 5. No, it's from the origin we'll take now. So 0. So 5 minus 0 is 5, and it is 10. So once, and this is 5 times. So 25. The upper part, it is positive. No, I'll mention positive. The down part now.
Answer is
You told 20 joules now. I'll keep it that one. Okay. 22. Okay. Now it's changed. You changed that 22. Okay, fine. Now down part. So 7 minus 5 is 2. So 2 into 5. It is
minus 10.
minus 10. Okay. Minus 10. So it is negative. No. Now the last part of the shape. So 9 minus 7 is 2, and this is 20.
Answer is 35.
So it is positive. Now what is the answer? 35. You got it? So it's not 20, it's not 22 also. It is 35. 35 joules. Take down. Done. We'll go for the next one. Completed? Yeah. So the next part of the topic is the work energy theorem for the variable force. We have seen the work done for the constant force, work done for the variable force, work energy theorem for the constant force. Like, what is the work energy theorem?
Total work done equals to
Yes, work done equals to change in kinetic energy. No, right? No. Now if they are asking for the variable forces, what will be the formula? Like, change in kinetic energy will be there, but for the work done, it is
different.
integration of from x initial to x final f into dx. Okay, the only thing it changes here. Okay, so derivation has been given there. Take a note of this.
Only formula or voltage.
Done. We'll go for the next one. Yeah. Okay. So next topic is potential energy. So as we have discussed, the potential energy is nothing but the stored energy, right? No. So it is a stored energy by the virtue of its position or configuration of the body. So suppose if I take an object from the ground, okay, I am raising to the height h. What happens here? For example, I am taking this remote, okay, from the ground level to the some height h1. h1 is 10 meter. And second case, what I am doing is the same remote I am taking to some height h2. It is 20 or 25 meter. So which one will have more impact?
25 meters.
Yes, no, obviously. And one more thing, the work done for h1 is greater or h2 is greater? Obviously h2 will be greater because I am doing more work, no, against gravity, like same weight only. I am taking the same weight, okay, but two different cases. One is 10 meter and one is 25 meter. So against gravity I am taking, right now. So the same cases here. So let us raise the block up to height h, the work done by the external agency against the gravitational force. So when I consider force and the displacement in the same direction, angle between them will be 0. So cos 0 is 1, right now. For example, this is the block, I am applying a force in this direction and the displacement also going in the same direction, angle between them is 0. Suppose force is in this direction, displacement is in this direction, angle between them is 180 degree. Okay, so that's the case here. So f h cos theta. So h is nothing but the displacement happened over there. Okay, so cos 0 is nothing but 1. Okay, so f is nothing but m into a, but what we are discussing it here against gravity, like due to gravitational only we are discussing, no. So acceleration will be considered as gravity. Okay, so mg h. Okay, cos 0 is 1. So work done will be mgh. So what will be the SI unit of this? Joules. Write it first, we'll go for the next one. Completed? Can we go for the next one? Yeah. So gravitational potential energy is the function of height and SI unit is joules and dimensional formula is ml square t power minus 2. So the dimensional formula for the work done, kinetic energy and potential energy are same. So gravitational force. So it is defined as the negative gradient of the gravitational potential energy and the formula is F is equals to minus mg. So the negative sign indicates that the gravitational force is downwards, like we are taking towards up. No, yes, no, like we are taking the object towards up, which is against the gravity, right? So A will be considered as minus G. So it is, the force will be minus mg, right? Completed, Siddharth. We'll go for the next one. Okay. So now the thing is, we have discussed about the work energy theorem. No, so what is the work energy theorem formula?
K initial minus K
So work done will be equals to change in kinetic energy. So similarly, work energy theorem, like we have discussed about the kinetic energy. No, now when we are talking about the potential energy, so work done will be equals to minus change in potential energy. It is minus change in potential energy, that's it. Okay. I'll write over here. So two formulas, minus change in potential energy. So when you see over here also the same thing, like V final minus V initial should be there. No, it is minus of minus will come. No, so minus of V final minus V initial, which is nothing but V final, so minus V final plus V initial. Okay. Done? Okay, we'll go for the next one. So conservative one, non-conservative forces. So the work done by conservative force such as gravity depends on the initial and final position. Okay, so the work done by the conservative force is closed path is 0. So simple thing, like when the path is dependent or path is independent, that's it. Okay, the state and path functions, that's the major thing, plays a role in conservative and non-conservative. The first point I should see whether it is path depends or independent. Okay, that's the first point. And I should see the whether initial position or final position. Like if you see the frictional, no, friction force is there. In friction force, I should consider the whole path. Yes, no, I should consider the whole path. Suppose for example, I am traveling for 2 meter. The second case I am traveling for 5 meter with the same object, and friction is acting over there. So the friction is same in the both cases. Okay. So when I consider this case and this case, in which cases the energy loss is more?
Second case.
In second case, because I am traveling 5 meter, the heat will be produced more in this 5 meter when I compare to this 2 meter. Yes, no? So I should consider the path when I am talking about the frictional force. Okay. So if work done by a force depends on the other factors such as velocity or path taken by the body are called as non-conservative force, that is friction. Grook. Why are you stopping, sir? Sir, please explain again. See, this is evening batch group, like people who are present in offline, no, they are taking notes also. So that's why I'm giving a gap in between, like 1 minute like that. Okay, I'll explain this conservative and non-conservative. Okay, once again I'll explain. So conservative and non-conservative. First I'll say about non-conservative force. So if a work done by a force depends on the other factors like such as velocity or path taken by the object. Okay, so it is non-conservative. Conservative means I am not depending on the path. I am depending on the initial and final position only. Okay, I am not depends on the path traveled. I am depends on the position, initial and final position. That's it. So when I consider the whole system, like this is the earth. If I take this point or this point, the gravity will be same, right? Yes, no, it is 9.8 meter per second square, right? No, but when I talk about the friction, no, when I talk about the friction, what happens here? So I'll consider two cases, that is 2 meter and 5 meter case, which I explained in the previous thing. Okay, now I'm taking the same object having a mass m and having a friction here, same friction. So in this case, what happens? So 2 meter produces less loss in energy, but 5 meter will give more loss in energy. Okay, because the path traveled is more in 5 meter compared to the 2 meter. That's it. So I'm not saying the initial and final position, I'm talking about the total path traveled. I'm talking about here only initial position and the final position. Okay. Got it, Grook? Done? Okay. Now the conservation of mechanical energy. What is the meaning of conservation? Conserved. I am conserving something. What is the meaning of that? I am not losing anything, no. Meaning of conservation is nothing but I am not losing anything. So the total mechanical energy means what? The sum of potential and kinetic energy, right? So potential energy plus kinetic energy is nothing but mechanical energy. So of a system is conserved if the force, if a concerned force are conservative. Means like initially I am having some energy, okay, that is 10 joules. I am doing some work there. Okay, at final also I am having the same 10 joules, which means energy has been conserved there. Right now, see for example, I am taking. I am talking about the object m. This object m having 10 joules now. Now I am taking the object to some height h or whatever it is. I am taking from one point to other point. So I am doing some work there, no. So if the object having the same 10 joule in the second point also, point A and point B, then what is the meaning of that?
Conservative.
The object energy is conserved, right? No. So potential energy, kinetic energy. For example, if we talk about initially the object will be having some potential energy, some kinetic energy, right? No, means potential energy initial plus kinetic energy initial should be equals to potential energy final plus kinetic energy final, which means I can say it is conserved. Okay. The total mechanical energy at initial should be equals to final. That's the case. Take a note of it. Oh, sorry. Done. Completed?
Yes.
Okay. So let me explain with the simple example over here. So conservation of mechanical energy. Okay. So initially I am taking a ball, okay, which is of height h. So initially what will happen, like I am taking the ball and leaving as it is, which means initial velocity will be 0, right? No, and the final velocity will be some v. Okay, so in between some velocity is there. Okay, I am considering at height small h, the velocity is vh. Okay, now what happens here? Here I need to take kinetic energy plus potential energy. Here also I need to take kinetic energy plus potential energy, and here also I need to take kinetic energy plus potential energy. Let me consider this is point A, point B and point C. Okay, I need to check whether point A, B, C everything are conserved. Okay, so what will be the kinetic energy here? 0, right? No, because velocity is 0 there. Yes or no? Velocity will be 0 and the potential energy will be there, and in between what happens here? Some part of potential energy will be converted to kinetic energy. For example, let me take here 10 joules is there. Okay, total mechanical energy. Here can I say like it is 2 and it is 8. If it is 2, it should be 8 only, no, if it is conserved. Then what about the final text? Again it should be 10. Yes, no, like whatever the energy at the starting point should be equals to the ending point, then only I can say that it is conserved, right? No?
Yes.
So now if you see here the total mechanical energy of a ball at height h, in the sense this is the height h, no, up to this, so it is mgh as a potential energy. Now when I talk about height small h, this is the height small h, no, the first one and the second one. So some potential energy will be there, kinetic energy also will be there. And when I talk about the ground level energy at the ground, which is of m v final square, so only kinetic energy. So everything should be equal, no, like if it is conserved, so I can equate it, eh and eg. So if I equate it, I can get the value of unknown things. Okay, so the meaning, like here we are doing for the conservation of mechanical energy only. Okay. Yes, sir. Sir, all the offline students also sitting in front of you. Yes, offline students also sitting in front of me. Okay, So we'll stop up to this and we'll continue with the next part of the chapter in the next section. Okay, bye guys, we'll meet in the next class. Bye.